So we're going to finish up talking about amines today and get into talking a little bit about phenols. So last time we finished off with the Hofmann elimination, which is basically the elimination of ammonia to form a carbon-carbon double bond. However, when you look at this slide, what you see is that the major product is actually the least substituted alkene of the two possible alkenes that we have. And so it doesn't follow Zaitsev's rule. It follows the Hofmann rule. And the question is, why is that the case? So let's look over here. I've got the example to show you step by step what's happening. In the first step, we're taking an excess of iodomethane and reacting it with this amine. That's going to form the quaternary ammonium salt, in this case a quaternary ammonium iodide. Okay? Iodide is not a very good base, right? Why do we know that? It's acidic. Okay, you're on the right track, but tell me why. The conjugate base is a strong acid. That's right. So that means that iodide is a weak base. And we need a stronger base to do an elimination, right? So what we do is do an anion exchange. So we react this with silver oxide and water, which you can think of as silver hydroxide. And you precipitate out the silver iodide, and that leaves hydroxide around. Hydroxide is a much stronger base. And when we heat this, using our little magic triangle, we get the least substituted alkene as the major product. Can anybody explain that to me? Why is that the case here? Why does this not follow Zaitsev's rule? Nope. Good guess, though. What does the base actually have to do? What's the mechanism? Huh? Okay. So the base actually has to abstract a hydrogen, right? There are two possibilities. We all agree? We can have the base abstracting this hydrogen, or we can have the base abstracting one of these hydrogens. Obviously, it's abstracting the one from the dotted line, right? Why is that?
Because there's more hydrogens to choose from.
That's true. There are more hydrogens here. There are two hydrogens as opposed to one, but that doesn't explain why in and of itself. It's exactly steric hindrance. If this base has to come in and abstract this hydrogen, this group is big. That almost looks like a tert-butyl group, right? And it's going to have to come in between a methyl group and this big tetramethylammonium salt. It just can't get there very easily, and so it attacks the hydrogen on the least substituted carbon, and we get these so-called Hofmann products where we actually have the major product being the least substituted alkene. So it appears that it's violating Zaitsev's rule, and in fact it is. It's following what we call the Hofmann rule, and it's because of steric hindrance in these particular cases. Now there are some practical uses for the Hofmann elimination. I'm going to give you an example that I used when I was a graduate student. So we started off with 1,4-dimethylbenzene. We reacted that with NBS. We used free radical conditions. What's the product going to be of that reaction? What's going to happen? I'm going to brominate one of the benzoic carbons. I'm going to replace one of the hydrogens with a benzene ring, right? And so that's what in fact happened. That reaction goes very, very well. We then took this product and I treated it with trimethylamine, which is a gas at room temperature, so it's a little complicated to work with. It stinks to no tomorrow. Smells like rotten fish. What's going to happen in this reaction? Yep, I'm going to get an SN2 reaction. The nitrogen's simply going to attack the benzoic carbon. The bromine's going to leave. And what am I going to form? An amine? Yeah, the tetramethyl, or trimethyl, excuse me, ammonium salt. And so now we have the salt. We've got the bromide. And then I took this and I treated it with silver oxide and water. And what's going to happen now? I'm going to do an anion exchange. I'm going to exchange what for what? What's going to be exchanged out? The bromide's going to be exchanged out and replaced with hydroxide. That's exactly right. And in doing that, we actually formed this so-called quinodimethane species plus silver bromide precipitates out. Okay? How did that happen? Nope, just one's brominated, right? But the hydroxide actually attacks this hydrogen, and those electrons go in and kick out the leaving group, and you end up with this system, okay? It's called an extended Hofmann elimination. What's weird about that product? It's pardon? Aerodynamic? Aromatic, okay. So, yes. You kept saying, I was like, is he trying to say thermodynamic? Aerodynamic. Yeah, so it's not aromatic anymore. So would we predict that this intermediate would be reactive or non-reactive? It's actually quite reactive, and it does two reactions, and the one that I wanted actually happened to be the minor product, but it's the one that we wanted. These things actually dimerize. They react with themselves and form this so-called 2,2-paracyclophane compound. That is two benzene rings that are stacked on top of one another, held together by these two ethane bridges in the 1,4 position. And you can't tell it here, but we expect benzene to be what shape? Planar and flat, right? A hexagon, but it's going to be planar and flat. And actually, these benzene rings are so close together that they pucker. But yet they still maintain some aromatic character. And so it's actually one aromatic system if you really think about it, because the two aromatic rings are really smashed together and they behave as one system. So when I do chemistry on one of the rings, the other ring knows that it's been done. And so that's what we were studying in the lab. And so we were using these 2,2-paracyclophane compounds to do some interesting stuff. And so if you happen to know Yusuf Dawood, he works in my lab. He's working with 2,2-paracyclophane. This is how you make 2,2-paracyclophane, or one way to make 2,2-paracyclophane. The yield sucks because this actually goes on and also forms a polymer. So you have a polymer and a dimer that gets formed, and you have to separate the two. But this material right here, when I was in graduate school, was more expensive than gold on a per gram basis. And so that's why we made it. We took the hit on the yield because we didn't want to buy it at the time because it was so expensive. But it's kind of a cool little molecule to play with. We won't get too much into that today. But we used a Hofmann elimination basically to generate the reactive intermediate that does this type of chemistry. Okay? So let's talk a little bit more about what we can do with amines. Amines will react with a molecule known as nitrous acid. And nitrous acid is generated very, very easily. You take hydrochloric acid, you take sodium nitrite, and these things react to form nitrous acid. Nitrous acid will continue to react with the hydrochloric acid that's present, so the OH gets protonated. Okay, this now becomes a good leaving group, and then water can leave, and you get what's called the nitrosonium ion. The nitrogen is positively charged, and since it's positively charged, it makes a good electrophile. And electrophiles like to react with what? Nucleophiles, right? And what's an amine? A nucleophile. And so nitrous acid reacts with amines very, very rapidly. Okay, and so an amine, like a primary amine here, will react with the nitrosonium ion that you form from this mixture and form what's called a diazonium salt, Rn2+. And then, of course, you have some counter ion out there. This reaction is very, very easy to do. The amine salts, or the diazonium salts, excuse me, I should say, actually fall out of solution quite readily. You can filter them and use them. They tend to be explosive, or they can be, so you have to be kind of careful with that. But usually if you have more than 6 carbons, they don't end up being explosive. But if you have like 4 or 3 carbons on the amine, typically you're going to have a problem. But this is a process that we call diazotization, and these diazonium salts are actually very, very useful molecules. Okay? The chemistry that we talked about with the sodium nitrite is actually a health concern for most individuals. If you're like me and you like to eat sausages, sausages are sometimes preserved with nitrites. It'll say that it's preserved with nitrites. Like sodium nitrite, it helps kill bacteria and keeps the sausage fresh longer. But if you eat the sausage, what's going to happen when that hits your stomach? What's your stomach contain? What kind of acid? It's hydrochloric acid. So what's going to happen as that sodium nitrite hits my stomach? I'm going to form the nitrosonium ion, which will then react with amines that are present in proteins. And it can create carcinogenic compounds. Okay? And so we're not going to talk a whole lot about that, but I just want you to know that this chemistry does have real relevance biologically. It's not just something that we do in the lab, but it is a reaction that does occur in your stomach when you eat those delicious tasting things. But they have to preserve them with a preservative, and typically, or not always, but quite frequently they'll use sodium nitrite or potassium nitrite to do that. Okay? So the chemistry is pretty straightforward. The amine reacts with the positively charged nitrogen. You form a nitrogen-nitrogen bond. This hydrogen is now acidic, and the chloride removes that. You end up generating HCl. So this is called an N-nitrosamine. These are actually carcinogenic. That's why it's not healthy to eat things that contain a lot of nitrites. But the N-nitrosamines can actually react further. They can react with the HCl, pick up a proton. You now have a situation where the next hydrogen gets eliminated. You end up with this nitrogen-nitrogen double bond. The OH, now that gets protonated again. Now you've got a leaving group and you get the diazonium salt. And this all occurs very, very rapidly in a beaker, and you can watch these things. These diazo salts typically just fall out of solution. And these diazo salts are actually useful in a variety of reactions. And so let's talk a little bit about some of those. Now, secondary amines will also react, and they form N-nitrosamines, and they don't undergo further elimination because they don't have a hydrogen here. And so it's these types of amines that actually are really problematic for you biologically because they can't eliminate to make a diazo compound. They just stay at that N-nitrosamine stage, which is the carcinogen. And so if you think about your proteins, you have a lot of secondary amines and amides and things like that that can react and form these nitroso compounds, which are not particularly healthy. Okay. Same mechanism, just can't do the last steps because you only have one hydrogen on the nitrogen. Okay. Now these diazo compounds turn out to be pretty useful for making a variety of other molecules. So for example, if you take this aromatic or so-called diazobenzene, as we like to call it, okay, this is a fairly useful molecule. You simply take this, heat it up in water, and you can make phenol. Because N2 is a pretty darn good leaving group. Okay, now the chemistry isn't an SN2 or an SN1 reaction here. We'll talk about the chemistry of phenols here in just a moment. But you can make phenols from aminobenzene by diazotizing that aminobenzene to the diazobenzene and then reacting it with water and heating it up. Now, quite frequently you will find that the reaction here is fairly slow unless you add a catalyst, and quite frequently people add copper catalysts. So in this case you would add something like copper oxide, and you can replace the N2 group with the OH. So it's a pretty convenient way of making phenols. So you'd boil it up in water with a little copper oxide, and that would work out pretty well. Okay? Another thing that we can do with these diazo compounds is we can replace the nitrogen with a halogen. So for example, if we take diazobenzene, react it with copper chloride, we can make an Aryl chloride very, very easily. How else have we learned to make Aryl chlorides? That would make an acid chloride. Iron trichloride and? So benzene, iron trichloride, and? Not aluminum trichloride. Just the iron trichloride. And chlorine. Right? So chlorine, iron trichloride, and benzene would make that as well. I would argue this is a lot easier for us to do on a laboratory scale. Why? No bubbling of gas, right? So it's a little more practical to start off with something like aniline, make the diazo salt, and then simply react it with the solid copper chloride to make the chlorobenzene if that's what I wanted to do. We can also do this chemistry with any halogen salt pretty much. We can take the diazo compound, we can react it with copper bromide, we can make the bromide. How would we have done this before? We would have used iron, tribromide, and bromine. Bromine's pretty, I mean, we can work with bromine, but it's still pretty nasty stuff. If you've ever opened up a bottle of bromine, this red fuming stuff comes out of the bottle. None of that happens here, so it's a pretty friendly reaction to do on a laboratory scale. I need to tell you that these reactions using the copper catalyst, or the copper, there's not really catalyst here, the copper species, this is called Sandmeyer chemistry, another name reaction. So when you hear the term Sandmeyer chemistry, you need to know that you're going to be taking a diazo salt and you're going to be converting it into some type of aryl halide. Okay? So we got chloride, we got bromide. We can also do fluoride and iodide, which we could not do with our previous chemistries, could we? Remember when we took aromatic rings and we put halogens on them, we were limited to bromine and chlorine. I told you that if we tried to do that with fluorine, it would go boom. And if we tried to do that with iodine, it just wouldn't work, doing the old electrophilic aromatic substitution chemistry. However, this chemistry works very well. It's just that you're going to have to pick a different reagent. So we don't use copper fluoride, we use tetrafluoroboric acid, which is a fairly strong acid. You take the diazo salt, you react it with tetrafluoroboric acid, and you will get the aryl fluoride. So now we can fluorinate the molecule. We don't have to worry about it going boom because we're not actually using F2. Okay, we're using tetrafluoroboric acid, which is a fluoride generator. Okay, we can also make the iodo compound by reacting with either sodium or potassium iodide. Again, making that carbon-iodine bond fairly easily. So this Sandmeyer chemistry is actually a little more useful than the electrophilic aromatic substitution chemistry that we talked about. I don't have to work with bromine. I don't have to work with gaseous chlorine. I can work with solids. I may have to work with a strong acid up there for making the fluorides, but nonetheless, this works out pretty good. Okay? So that's Sandmeyer chemistry. Now, if we look at this particular problem, here we have an aromatic ring and we want to put 3 bromines on there. What's the problem with that overall? Why should that make you cringe? They're all meta, aren't they? And we know that bromine is a ortho-para-director, but it's a deactivator, right? So number one, the positions aren't even right. They're meta to one another. And 2, it would probably be hard to put 3 or 4 bromines on an aromatic ring using the electrophilic aromatic substitution chemistry because it's a deactivator. We could probably put 1 on and maybe 2, but getting that 3rd one on might be difficult, right? Or that 4th one, whatever we wanted to do. And so we're going to figure out how we can do this using this type of chemistry, okay? This diazo chemistry. So if we think about this, I need to get those bromines in a meta position. So you might be thinking I need a meta director on there first that I'm going to remove later. Not true. What we need is we need an ortho-para director on there that we can get rid of later. What's a good ortho-para director? That's activating. Pardon? Alkyl groups are? What else? But alkyl groups might be tough to get rid of, right? How about an amine? What is it? It's an ortho-para director, and it's a strong activator, right? So what we can do is start off with the aniline, react it with bromine in the presence of iron tribromide, and it will put the 3 bromines on for us very, very easily because it's a strong activator. Now notice, this is going to be the directing group, right? And so it's going to direct the incoming things at the ortho and para positions. But if I imagine removing the nitrogen, now all of the bromines are meta to one another, aren't they? So I've got to remove this group. And the easiest way to remove that group is to convert it into a diazo compound and then replace the nitrogen with a hydrogen. That's all I got to do, right? And that's pretty easy to do. Actually, it's quite easy to do. So what we're going to do is we're going to start off with benzene. We're going to do electrophilic aromatic nitration and put a nitro group on it. We're then going to reduce the nitro group. Here they show using hydrogen and palladium on carbon to get the aniline. What other groups could we have used here to do this reduction? What other reagents did we talk about last time that we can reduce nitros into amines? Technically, LAH will work, but it's not what we talked about. It's a bit overkill. Well, iron or tin and hydrogen chloride. So we can use the metals like iron or tin and hydrochloric acid. We can do that as well. That's going to be a lot cheaper than using palladium on carbon. Now I have my aniline. I do my bromination. Now I've got the 3 bromines exactly where I want them. Now I've got to figure out how to get rid of this amino group. So I'm going to diazotize it using sodium nitrite and HCl. I just made the diazo salt. And now I reduce it with this molecule. This is called hypophosphorus acid. It is a good hydride donor. And it works really well in this reaction. And the hydrogen replaces the nitrogen of the diazo compound, and you end up with the final product. Okay? So again, there's not a whole lot of new chemistry here, really. But, you know, how we put different reactions together and in what order determines what our final product will be. Okay? So again, more tools in our toolbox to do these types of reactions. These diazo compounds are useful for more than just Sandmeyer type chemistries. We can also use the diazo species to actually form carbon-nitrogen bonds and form these so-called azo compounds. So you have an aromatic ring, nitrogen, double bond nitrogen, another aromatic ring. Y here is usually some type of activating group like an amine or a phenol or something like that. It's usually a strong electron donor so that this reaction will couple correctly. And so this is, we're not going to talk about the mechanism, but the important thing about this is that this is how we make synthetic dyes. Chances are right now your clothes are the color that they are because of some diazo compound. Okay, so if it's your salmon colored shirt or if it's, you know, your aqua color, there's some diazo compound or mixture of diazo compounds that they've used to make the dye. Okay, and so butter yellow, this one right here, was actually used once a long time ago to color margarine. Margarine is synthetic butter basically, and it looks like lard. It looks like a white blob of Crisco. Nobody really wants to spread that on their bread, right? So butter is yellow, right? So they added this so-called butter yellow dye to it to give it the appearance that you were eating butter, okay? They no longer use these diazo compounds like this to color foodstuffs for the most part because they can be quite toxic. These diazo compounds can actually be quite toxic. So they've kind of avoided that. There are diazo-containing drugs. So if you suffer, for example, from UTIs, you know, the stuff that you take that turns your urine blue, that's a diazo compound, and it's medicine in that case, okay? And it works by a variety of mechanisms that we won't go into, but these diazo compounds do have a lot of practical uses. And so just a few weeks ago, if you were coloring your Easter eggs, you were probably using a diazo compound to give those eggs their color. Okay. So those are the synthetic dyes. All right. So we need to get started in on talking about phenols. One of the things, and I apologize for this, chapter 21 in the new book is not phenols anymore. It's this transition metal complex stuff. We ain't talking about that. Okay, we're going to start talking about some phenol stuff. And phenols are a useful class of compounds. We know what a phenol looks like. It's an aromatic ring with an OH. Has a lot of similar properties to alcohols, but one of the big differences of a phenol to an alcohol is its acidity. What's the pKa approximately of a phenol? About 10, right? So we have a pKa somewhere around 10, depending on what the substituents are. We can actually make it more acidic than that. We can make it more basic, depending on what we attach to the aromatic ring. But phenol by itself is generally accepted to have a pK value of around 10. And so would you consider this a pretty decent acid on an organic scale? Yeah. We can deprotonate these with sodium hydroxide. We can do all kinds of chemistry with them. And so being able to prepare phenols is actually a very, very useful process. And so we learned just a few seconds ago that we can make phenols by taking aminobenzene or aniline and diazotizing it. So what do I need for that again to make a diazo compound? I need sodium nitrite, NaNO2, and HCl, right? And that'll make the diazo compound. And then we would simply take this and react this with copper oxide and water, heat it up, and we can get the phenol pretty easily. That's a couple of steps, however, but it is a possible way in which you can make phenols. You can also make phenols by what's called the Dow process. Why do you think it's called the Dow process? Dow chemical. That's exactly right. This is an old process. It's no longer utilized anymore, and we'll talk about why that is. But this was Dow's process for making large, like tons of phenol on an industrial type scale. And we weren't talking about, little laboratory kind of scales here. And so what the Dow process is taking chlorobenzene, which is readily available, easy to make, and they reacted this with sodium hydroxide in water at 350 degrees Celsius. What's the boiling point of water? 100. So this is 3.5 times that value, right? So how do we get to 350 degrees Celsius if we're in water? Pardon? No, it won't it would just boil out the water. But we can increase the pressure, right? So remember, boiling point is dependent on pressure. So this is high temperature, high pressure. Not right off the top of my head, I'm sorry, I don't remember what the pressures were. But they were doing this under extreme pressure and extreme heat, which you can do on an industrial scale. You got this big plant that's made up, and then all this natural gas coming in, and they just heat it up until the reaction occurs. That's how industry likes to do things. And after workup, so they did this first, and then treated it just with mild acid at room temperature, and you get the phenol, and you can get tons of this stuff pretty easily. How did this reaction happen? What do you think the mechanism is for this reaction? Okay, so tell me how might I push those arrows? Okay, so hydroxide, you're proposing, under these conditions, would attack the Aryl carbon and what? And kick out the chlorine. Okay? If that's true, we should be able to do an experiment to prove that. How might I do an experiment to prove that? Okay, I'd probably have sodium chloride left over. That's one measure. But if chlorine's the leaving group regardless, I'll probably end up with sodium chloride, right? So that in itself isn't going to tell me that carbon was attacked by the hydroxide. How might I do an experiment to prove that or disprove, whichever the case may be, that that carbon was attacked by the hydroxide. Pardon? Could if we had stereochemistry.
You run it no more, because if it only attacked that carbon, then you would see symmetry about the other carbons and no carbon NMR.
You're close. It does have to do with carbon NMR. But I've got 6 carbons that, if you think about it, no matter which one got attacked, if the chloride left, I wouldn't know. I could tag the carbon. That's exactly right, and that's what they did. So they tagged this carbon with C13. They made that carbon enriched in C13. How they did it, I don't honestly know right off the top of my head. It seems pretty complicated to me, but they did. Okay? And so if this is truly the mechanism, if this hydroxide attacks this carbon, then when Aaron looks at the NMR, that phenolic carbon would be the one that's labeled with C13, and it would be the largest peak in the spectrum, right? Because it's 100% C13. However, when she goes and runs that carbon NMR spectrum, she sees 2 peaks of equal intensity. 2 carbon peaks. One where the carbon-13 is on the OH, and one where the carbon-13 is not on the OH, or connected to the OH, I should say. Huh. So it can't be what looks like an SN2 process, right? And we know it can't be an SN2 process because it's an sp2 hybridized carbon. The nucleophile can't get behind here to kick that leaving group out. None of that is consistent with an SN2 process. So how else do we account for this?
Do you heat it up high enough so that the hydrogens on the other carbons are more acidic? So then the base would attack the...
Okay, you're on the right track. You're on the right track. So sodium hydroxide at 350 degrees and high pressure, it is really basic under those conditions. We're really putting a lot of energy into it. Okay? It becomes really, really basic. And so what happens is you do an elimination of one of these ortho hydrogens, and you get a molecule, and there's our labeled carbon, that's called benzyne. And I'm going to put it in brackets here because it's an intermediate. What's weird about benzyne? Why? It's not anti-aromatic. It is still an aromatic compound because the other pi bond is orthogonal. So I have not made it anti-aromatic. Triple bond's supposed to be linear. Ahmed, do you have something you wanted to? It does because the hydrogen's now gone, right? There's no hydrogen here or here. There was never a hydrogen here, and we're eliminating this hydrogen as HCl. Okay? So we get this intermediate called benzyne that then gets attacked by hydroxide. We got a lot of hydroxide around, right? And just like John said, that carbon-carbon triple bond does not want to be bent. It's very, very reactive. And it can actually function as an electrophile under these conditions, not as a nucleophile. We normally think of pi bonds being nucleophiles, not electrophiles. But what happens here is the nucleophilic hydroxide will attack one of these carbons. And what are the odds of attacking one of those carbons? 50-50. And I'm just going to show one of them. And so you attack, let's say, the labeled carbon. And then I get a negative charge, and what happens there? It gets protonated by the water. And I end up with a phenol. And Aaron would have seen the phenol where part of it was with the label there, and part of it where the label was here. That is the Dow process. We're going to talk more about benzyne later, like on Friday. Benzene is a useful molecule. You can generate it. You can't store it, but you can generate it and immediately consume it and do other things with it. And there are many ways in which you can generate benzene. Everybody have what they need? Okay. So that's the Dow process. Now, the Dow process, phenol is cheap. And the Dow process is expensive. Why is the Dow process expensive? It's got to be really hot. You got to use a lot of energy to get it that hot. You got to keep it under pressure. So you can't just use a normal flask. You got to, I mean, we're talking about stainless steel reactors that are inches thick to hold the pressure. These things can rupture. People can die by using them. It's a pretty intense process. But it worked. There is an easier process called the cumene process, where you start off with cumene, which is just isopropyl benzene, very inexpensive. And you react this with air, with some type of free radical initiator. I'm going to just put IN there. Doesn't matter what one you use. Followed by mild aqueous workup, little acid. And what you get out of this process is phenol plus acetone. Why is this a more practical approach than the Dow process? Why? I don't have to spend a lot of energy making it hot. As far as I know, air's still free, right? So these companies just blow in air from the outside. That's where they get their oxygen, right? Water and a little bit of acid, cheap. But also look at my products. Both of my products can be sold. I can sell phenol, and I can sell acetone. You guys go to Lowe's or Home Depot, you buy acetone as paint remover to clean your paint brushes. Ladies, you use it to remove your fingernail polish, whatever the case may be. Both of these products are marketable. You can sell them, okay? So everything that you put into the system comes out into a product that you can sell. That's a good thing. Now you might say, well, the Dow process generated salt. Yeah, but I don't think anybody's going to take the salt that's been in all those chemicals and actually spread it on their, the French fries, okay? So probably not going to do that, all right? So everything that you get out of this process is sellable. So let's work through it. How does this work in? What's the first step? What's happening in the first step? Pardon? We are going to get a radical reaction. What's the product of that going to be? Here? Yep, we're going to generate a tertiary radical. And it's more than just tertiary. What else is it? It's benzoic, so it's pretty stable, easy to make. What's going to happen with that radical? What's it going to react with? It's going to react with the oxygen. Oxygen's a what? It's a diradical, remember? Each oxygen atom has a lone electron on it. So we know that radicals react with one another. So once we generate this radical, it reacts with the oxygen. I'm just going to show the lone electrons. Now what happens? This is the propagation step, right? So what happens now? Does that oxygen radical just sit there? What's it going to react with? I got a lot of this, right?
Oh, so you can keep doing it, right?
Yeah, I got a lot of this. Initiators, we just use a trace amount, right? So this reacts then with the cumene I get what's called cumene hydroperoxide. Plus I get another cumene radical, which goes back and reacts with oxygen. So this continues. But cumene hydroperoxide is what we get from step 1. This reaction is so easy to do, it happens without us knowing it. So in my laboratory, we have a bottle of cumene that has been sitting around for several years. If I went and tested it right now, it would test positive for peroxides. And it would have formed cumene hydroperoxide just by sitting there for years. So it's an easy thing to happen. You don't even really have to work at it. Okay? So anyway, this is what you get from step 1. Is that phenol? Is that acetone? No, but look at the atoms. I have all the atoms I need to make phenol and acetone. I just have to do some rearrangement. So what happens is when Aaron takes this mixture and dumps it into the acid, something interesting happens. So you take the cumene hydroperoxide, you dump it into acid. What's going to happen? Okay, which oxygen? The one with the hydrogen or the one without the hydrogen? Got a 50-50 chance on that. You're right, yep. So it gets protonated. Now what happens? Water is a good leaving group. Will it just leave? No, something's got to push it out. This is where the rearrangement comes in. What do I actually have to change? What do I have to rearrange? What bond do I need to make? Think about the products. Right now I have no aromatic ring oxygen bond, right? In this. I mean, and that's what I need, right? So what happens is, and this is kind of slick, the aromatic ring migrates and attacks that oxygen, and that leaves. Who knew? Right? And in doing that, you get a bond that looks like that. And you get that carbocation. Now what happens? It's already rearranged. What happens? I've just made the carbon-oxygen bond I need. I've got a carbocation and I've got water. What happens when carbocations come into contact with water? They get hydrolyzed, right? And they form alcohols, right? So this water now attacks the carbocation, and I'm not showing all the details here, okay? You all can figure that out, because there has to be a proton transfer too. But I end up with this. What functional group is that? Carbon atom sharing 2 oxygens, one being an ether, one being an OH. It's a hemiacetal. It's close to an acetal, but it's a hemiacetal. What do y'all remember about hemiacetals? When we were doing the reaction with the sugar, remember we did the demo, made the mirrored flask? The hemiacetal was closed, or it could be open. And when it was open, it was a carbonyl, and when it was closed, it was the hemiacetal, right? Same thing happens here. This simply collapses to give you the acetone plus the phenol. because hemiacetals will do that, right? And since there is no ring to help keep it together, it just spontaneously falls apart and gives you acetone and phenol, two products that Jack can then separate easily and sell and make a load of money.
What's this reaction called?
This is called the cumene process. Yeah, it's not really a named reaction. Okay? Last one that we're going to talk about today for making phenol, or phenols, is the Baehr-Villiger process, the Baehr-Villiger reaction. We've talked about that one before. So just to change things up a little bit, I'm going to put a methyl group out here, and we've got this ketone. The Baehr-Villiger reaction, what do I need for the Baehr-Villiger reaction? Anybody remember? No? Yep. MCPBA. I need a peroxy acid. MCPBA is the one that I like to go to, but any peroxy acid technically will work. And the Baehr-Villiger oxidation takes ketones and converts them into esters by inserting an oxygen atom in between the aromatic ring and the acyl group. On Friday, we will do some in-class problems as an inverted lecture. You all need to know that reaction mechanism, so start studying up on that. Okay, how does that happen? This kind of looks like a phenol, but it's protected as an ester. So how can I take an ester and get an alcohol? I could reduce it. You're absolutely right. I could reduce this with lithium aluminum hydride or sodium borohydride, no, lithium aluminum hydride, excuse me, and I could get the alcohol. That's pretty dangerous. There's an easier way to do it. What were you going to say, Ahmed? I could, but I can make R just simply water, another H. We can hydrolyze. And so we can take sodium hydroxide and water followed by the normal workup, and I can hydrolyze the ester to the alcohol and the carboxylic acid. Acetic acid, I can sell that. The phenol, I can sell that. Okay? What do we call it when we hydrolyze an ester in the presence of base? It is saponification. So you're going to saponify this. Could I have reduced it with lithium aluminum hydride? Yes, but that's overkill. Okay? Could I have just treated it with water and boiled it? Yeah, but reaction would have been fairly slow. Saponification? Don't ask me to spell out loud. I'll always mess it up. I got to write it down. Huh? Yeah, which we got. But you also have to remember you get an alcohol. In this case, the alcohol happens to be a phenol. All right, so that's it for today. I will have your inverted lectures that you turned in on Monday to you on Friday. I'm going through on those just to give you, everybody's getting points if you worked them, but I am making comments. So you'll want to look at the comments, okay? Most of you got it in the right ballpark, but there are just some little details that you need to think about. See you all on Friday.